I'll give my acknowledgments. A lot of the following slides and some links to news are given here, given by Dr. Phil Barth, Professors John Kumi, Terry Root, and Ken Caldera. So here is the greenhouse gamble. There are a small chance of having very few ecological impacts. The predictions have gotten harsher. What does that mean? That means the first time that I checked out this MIT policy group's wheel of misfortune, as they called it, this is a nice way of communicating probability wedges to a lay audience, right? And what you can do, we'll do it in a second, is you can click on it. The probability wedges are, you're more often going to end up with something that has a large probability wedge than something that has a teeny one. When I started to get worried about climate, it must have been around 2006, 2007, and found this. This is what this circle looked like of what we expected for temperatures with no policy changes. Guess where we are now? So the chances are very, very slim that for what we had most of this, the chances are very, very slim that our temperature rise will be this small. So let me see if I can find that in my web browser, which I was trying to have it up here. And if it will kindly allow me, I may be signed in. We might be good. Yes, there you go. Are we going to win or lose? We got off pretty easy this time. So it's an interesting interactive tool. And what this particular pairing is showing is what's happening with no policy or with the policies that this particular center studying policies at MIT advises. So that's kind of an interesting tool to see. Why do we care? Why on earth don't I put this on full slideshow? This is a brilliant graphic that shows, why do I care if I've gone up 1 degree C? I live in Canada, I live in Minnesota, and I'd personally love it to be a little bit warmer, right? But the answer is no. This is a graphical representation of what came out of the IPCC 2007 report, Intergovernmental Panel on Climate Change, many, many climate scientists working together. And already you get this kind of things we have. Decreasing water availability, increasing drought, increasing wildfire risk. Does any of this sound kind of familiar? And then the black are the ones that really caught my attention. Greater risk of extinction. I mean, and this was a group of scientists deliberately trying not to be alarmist. So greater risk for 20 to 30% of known species. By the time you get up here around 5 degrees C, which it looks very likely we may get to, they're not saying greater risk, they're saying extinction of, nearly half known species. It's that kind of thing that keeps me working on this, though this is pretty much the volunteer job. It's important. And I've got to say, it's a wonderful thing to work on something that you personally think is that important. I don't know, it adds a certain kind of joy, even though it's a kind of grim topic. This is just kind of the mechanism of why is it getting warmer. Basically, we change the atmosphere, the composition of the atmosphere, and it equilibrates at a slightly different temperature than what we've historically had. This other graphic, which we're going to power through because I realize I am luxuriously taking my time, but we've got a lot of slides, is what are really the sources of, and so when I post these slides to our class set, you will see all these nice links. So what's our temperature like? What's really warming the world? And then you can page down and see, is it Earth's orbit? All the things that people say it can't possibly be greenhouse gases, right? And as you go down, is it volcanoes? Is it all of these combined? It's like, no. And you finally get down to deforestation, ozone, aerosols, greenhouse gases. Those other things actually reduce temperature a bit. Greenhouse gases are a bit more than that. And when you add all of that together, you get a pretty darn good fit to the model. So there's a number of things that are showing that it's pretty incontrovertible. As opposed to when I first started teaching this, when there were a lot of people arguing about this, it seems that more and more understand, no, this is a real problem. So what are we going to do about this is really the question. And this is from John Kumi's book, Dr. John Kumi's book. This really is a pretty brilliant book that I strongly recommend. And his thought is, think about what if we say, it's that assume the solution thing. assume we have to not exceed the 2-degree C limit. You saw there's still some pretty dire problems at 2 degrees C, right? That's still pretty, we're still having a greater risk of extinction for a lot of species and a host of other problems, many of which we're seeing today. But it's better than if it gets worse. What do we do? And he's presenting CO2 data that you can get from, 800,000 years ago to now and see that we are running a rather unintended experiment on our own atmosphere. And, what happens? What happens in the no policy case if we're doing greenhouse gas concentrations? You can read this in the book. You can keep looking at this. But you can see that every time that people are saying, well, if we put in a policy to do this, what would happen? It turns out that we tend to exceed that goal. So far, we've been exceeding it. It's because there really isn't the political and cultural will to take this on and do it. And so the latest IPCC, the 5th assessment report is out. You can read it, and you can see, CO2 continues to go up. Arctic summer sea ice goes down. Temperatures are going up in the ocean. Sea level is rising. It's what you would think. The thing that this report gets critiqued for more often than anything else is that it's too conservative. Again, scientists are trying very hard to not be seen as alarmists. They really want to be sure of their facts before they're talking about this. And sometimes it makes it sound, to somebody who's comfortable in their current life, well, they're not sure. Well, so it's actually a little bit of a problem. Here is a scarily prescient ad from 1962. One of the old oil companies talked about, and they were proud of this, of course, because one of the big fears back then was that we were going to slide into another killing ice age. This actually was one of the fears back in the 60s. Each day we supply enough energy to melt 7 million tons of glacier. Wow. And they were probably right. Wow. And so there's a number of links that you can dig out if you're looking at the slide set after I post it on coursework of just, there's a lot of confusion, but there's a lot more, even in the confusing, really good science here. Now the oceans are uptaking more CO2 again. That would be good news until suddenly they're not, right? I mean, that's one of the large ununderstood things is how much of a sink do we have here? Is it a 2,000-year turnover or 5,000-year turnover? What will happen? But you can follow these links yourself and see what you think. Sea level will rise by 1 meter. It's unavoidable. All of these links that I'm going to show you in the next few slides that are in this sort of format are just over the last couple months. I mean, the news has exploded in this area. Arctic sea ice loss likely to be reversible. It's like, whoa, if the Earth gets cooler. Still, that's very good news. If we could cool the planet, we could get the ice back. Why do I harp on ice? I'll get into this more in a bit, but as summer Arctic ice disappears, we are losing our ability to reflect the incoming summer sunlight. And back when I got concerned in 2006 and thought, what would I work on to help this situation? People were talking about that one effect was responsible for about 20% of global temperature rise overall. Now, the latest that I've heard from hanging with the climate scientists at the AGU meetings is it's more like a third. So more like 33% of global temperature rise comes from the fact we don't have much reflective ice anymore. So that would be very good news for continuing to cool the planet a bit instead of have this runaway as we're having now. And why do we care? Well, again, it's more and more in the news, especially this last year or two, how very much it costs coastal cities per year to try to shore up against rising seas by doing simple things like building levees or make sure that their outfalls come out above water level somewhere. I've been advised there's more and more data, more and more estimates because people are actually building it. There's good old New York City at $2 billion a year. And there's lots of other data points, but I've been told don't put too many there, but it isn't because they aren't there. And yeah, of course, graphic artists have a good time communicating this. This hasn't happened yet, but it's the sort of thing that concerns people. And right now, the cost is billions per year per city to deal with these very fundamental issues. After 2050, the projections are as more and more ice has melted and sea level rise becomes more and more rapid, trillions of dollars. So it's one of those expenses that you would be so much better off doing some prevention rather than trying to cure after you've, of course, ruined a lot of people's lives. More, fun from the graphic artists, but boy, it paints a picture, doesn't it? This is a scuba diver in the New York subway system. It's, it makes you think. And then there's all kinds of, fossil fuels news. Again, over the last couple months, that oil advertisement I showed you, burning all the fossil fuels could melt our Antarctica entirely. It's an interesting headline. Flash credit scheme backfired. Apparently some rather phony, fictitious exchanges being done on, how you can get a carbon credit for things, but this one was phony and the greenhouse gas emissions were actually more. Elon Musk talking fossil fuels, yes. And the Sun Edison solar farm beating natural gas. So there's good news. Part of the joy of seeing this more and more in the press in a more and more balanced way is there's more attention and there's more good news to point to. This is a fascinating one that we don't have time to delve into, but it's showing how all over the United States, how our energy is generated where we are. That is a very fascinating chart, which you might want to check out. This is a scary one. If we continue to burn fossil fuels, of course, we have more and more CO2, and they're warning, this particular group of scientists is warning that there is no CO2 techno-fix, even with the CO2 that we have already in the oceans and in the atmosphere. We've acidified the oceans and warmed them considerably to an extent that it would take a very, very long time to recover, even now, if we stop now. That is the stuff that could certainly paralyze you if you dwelled on that. But again, let's try to think our way through solutions. It means we have to change our ways pretty quickly. And how we're going to do that, I don't know. There's some people who have great hopes for the meetings later this year in Paris. We'll see. The jet stream has become destabilized because, again, climate scientists tell me this, because we don't have the steady driving force that we had historically, of very, very cold up there at the North Pole compared to the rest of the world. So you can imagine that you have a less of a delta between those two regions, and you've historically had this nice, stable jet stream through most of human history. And what you have now is less of a driving force, less of a differential. So if there's any perturbation whatsoever, you start having the jet stream change its configuration. And that means that you get unusual weather patterns that we haven't had before, like what's happening in California right now. And then that part must be in a timer or something from an old slide set. And then it will suddenly change to the other configuration. So suddenly then you might get really heavy rains. It's over the course of human civilization, again, what I've heard at the AGU is that over the last 10,000 years or so, we've had an extraordinarily stable band of a couple of steady jet stream configurations where we could count on, basically, where are we going to live? Where are we going to plant our crops? And we don't have that anymore. And you can see we're getting more and more severe storms with horrible human costs. It's not good. And then we've got, it's getting hard to deny these hottest summers, coldest winters that are happening for most of the Pacific Northwest. Again, go on the site and follow these links if you want. Heat and drought, cooking fish alive, 1.5 million fish of one species up in the Pacific Northwest. And people getting desperate enough to put big black plastic balls on their reservoirs to reduce evaporative loss. Now that sounds kind of interesting, but I will tell you that this particular piece of news is actually good news for me. So stay tuned. And then climate change and politics. This is actually a hopeful read, this top one. The year humans got serious about climate change, right? Because that's what it takes before we can get somewhere. And then various you know, political figures saying things they should or shouldn't or denying this or that. But Obama making an urgent appeal, he went to Alaska, making an urgent appeal for climate change action, right? How some of the dynamics of how people reinforce each other's opinions that there's no problem is really fascinating. How to get people to care. Jason Box, one of the heroes of climate change, really. He was one of the guys who put all the cameras, or many of the cameras, out in distant, distant cold places to film the disappearance of ice for that really impactful movie, Chasing Ice, which if you haven't seen it, do. Just a great climatologist, has basically gotten so despairing about the atmosphere of denial in the US. He has moved his family with his three-year-old daughter and his wife to Denmark, where he thinks maybe they've got the best chance of surviving the climate onslaught. I mean, this is a guy who was tacking plastic sheets on Greenland, trying to see if that would slow the melt. This is a passionate, dedicated, expert guy, and he's, you know, from the interview that I was reading in the Huffington Post that this will point you to, or I guess this is one that is related to it. You know, he's just given up, and that's scary. But we don't have to. But before we go to the hope, let me share with you a little more bad news. Professor Terry Root was married to, is the widow of Professor Stephen Schneider, who is one of the really outspoken proponents of letting people know about climate change and what's happening and why it's a problem. And she was one of the early encouragers of my own particular work. She and Steve, both of them. And she is, she's an expert on the pressures of climate change on species. Why does it hurt your species if it gets a little bit warmer here? And so she will do a much more eloquent job than I can here. So look up her video. But she talks about basically how the species interact. You can imagine if you, the predator for this particular species, that species has moved away someplace where you can't adapt to. Your food has gone. You have to go another direction because you're tolerating the cold or the heat differently. Things just start really getting in a bad way for species to survive. It's part of why we're in the 6th wave of extinction, why we are going rapidly off this cliff. And this is a beautiful little tale of introducing or killing off wolves, coyotes, red fox. Now you're reintroducing them. It should all work, right? Because you know who eats who, who's preying on who. And it's such a colossal mess when humans interfere without all the facts. So one of the keys that I take away from all of this is, actually Steve Schneider used to say this, is that you do not do something that wouldn't make sense just because you're desperate. You make sure that, you know, if I'm going to stop burning this or I'm going to make this particular source or that it has to actually make some rational sense. You know, if you just say, oh, there's too many wolves, let's introduce coyotes and see what happens. You've actually got to figure it out first. It tends to be more complex than you think. And so the types of adaptation that species do are they're shifting their ranges to either go, you know, up or down towards a pole where it's colder, or go up in elevation. And as I say, things change, migrate at different rates. For instance, plants aren't going to migrate nearly as quickly as animals that might be used to feeding on them do. And so you're ending up with, you know, this thing where one species is going in this direction, another in that, and you're just ending up with a mess. Everybody's starving. You've suddenly run into a new predator. You have no food. Things are blooming at the wrong time. And so right now, the background extinction rate has been less than one species in 1,000 over 1,000 years. Our current extinction rate is about 1 in 10 over 1,000 years. So less than 1 in 1,000 to 1 in 10, which is alarming. And so going back to that thermometer, that rising thermometer of doom that I showed, if we're up 3.6 degrees Fahrenheit, expecting 400,000 species extinctions, up 7.2, which is not inconceivable, 1 million species extinctions. So this is, you know, this is alarming. This is our web of life. So what are we going to do? You know, here's Calvin and Hobbes thinking about giving up, right? I think it's big enough you guys can all read it. So is that an option, leaving? Actually, more and more in the news it is, right? People are saying, okay, we're going to go colonize this. Okay, that sounds like a long-term plan. So here's our challenges. You know, you guys, if you like challenges, you've got a lifetime of work ahead of you, which is magnificent if you happen to like challenges. So some insights from Cold Cash, Cool Climate. You know, our choices for response to climate change are mitigation, adaptation, and suffering. Climate problems big, urgent, misunderstood, and therefore fertile ground for starting new ventures. And then I love what his focus is. This is why I love this book. Rather than one simplified response, rather than assuming that we're going to come to the political accord that anytime soon that's going to unify the planet and go in the right direction, entrepreneurs, knowing what they're doing, knowing what the site is, like the founders of Tesla, you know, let's get us off fossil fuels and have electric cars as an option. I mean, that was really their vision when they founded that. Try things, fail fast, do all the things entrepreneurs do, and that can make an enormous impact. You know, you might be trying over in water conservation, you might be trying in more efficient farming, you might be trying in different kind of power, and together can actually make an impact while whatever political process is going on goes on, which may be too slow. He also says the forecast, you know, as you say, well, we're doomed. Underestimate this particular factor, the factor of the entrepreneur, the factor that you can have people of independent thought and creativity going along and, you know, making an impact. And so that too should give you a little bit of hope. And so here he is, assuming the solution. Okay, we're not going to exceed 2 degrees C. How do we get there? I mean, that's the next step, right? Once you know you can do this, you know you can do this. Okay, how much can we keep emitting? What's our limit? You define the pathways, you assess what's possible, and you try various options. But you try them sanely. Let's not introduce wolves and coyotes and watch and see whether that worked. You know, try things in a way that's not going to have a negative impact. The other thing we're fighting is that most of our infrastructure has been built, you know, right now is pretty aging, and most of the 2050 infrastructure, so the stuff we're going to have 35 years from now, is going to be built between now and then, right? It's not like we're going to have stuff from the 1800s doing that. So as we look at this, green building, for instance, which we have a talk on, I mean, that's really important. That we have a chance to build things now that are going to be what are affecting our future in 2050, right? We can do it right now. So do it now, right? Waiting just costs more. We turn our billions per year into trillions. Let's make sure that we're looking at the same things. Start small, think big, get going. I totally agree with that. Of course, your other option is just doing nothing, which in some sense feels like what much of the world's been doing, right? And then you know what all these impacts are, right? You've seen them. And we're living a lot of this, right? Higher temperatures, fires, you know, it's droughts. So what are the options here? So rather than do nothing, we can try to cure it at the source. We can change our energy mix. We can adapt to rising sea levels. We can invent new energy sources. A lot of people look at geoengineering. And geoengineering is a fascinating combination of things that, at least to my mind, some make a lot of sense and some really worry me. And you can see over here a collection of, you know, the guy who proposed trillions of orbiting solar lenses. Okay, if you can fend off incoming sunlight way, way out there, it will keep things cooler, but, you know, how do you undo that if you decide that's wrong? How about if you decide you wish you could grow food here again, but it's shaded? You know, there are just things there that worry me a little bit, right? And you can go through these options and see. I mean, it's wonderful to come up with these ideas. I think for an exercise, we should come up with some ideas as well. But we really have to think them through before we risk a lot on them. So some look interesting, some have really risky impacts. And the ones that really worry me are the ones that can go worldwide very quickly. Some people look at that as a real feature. I don't. I think it would be nice to do things on a local scale that you could undo. You could reverse if you decided something was wrong, because humanity is very good at not quite realizing all the unintended consequences. So if you do things in a way that you could undo them, that seems to me extremely prudent. Geoengineering involves these very complex issues. Some of the complex issues are the moral hazard, which is that if I assume that some genius over there is going to be able to fix it all, then I can keep on driving a 10-mile-per-gallon gas hog, as far as I want. And I can live a very CO2-producing lifestyle and know that my kids don't have to worry because somebody else is going to fix it because geoengineering is going to work. And that really is a hazardous mindset. Here's the Earth's energy balance, and some of these are what people are thinking about changing. So anybody who's talking about reflecting things from the surface, so the ice that's disappeared doesn't get to reflect as much. Some are talking about reflecting from changing where clouds are or having more clouds. I think you would mess with the water cycle at your peril, and besides which, there's an awful lot of heat exchange that happens here. And here's our whole, greenhouse gas effect of what are our radiations and re-radiations as we change the composition of our atmosphere. So staring at things like this, with how much energy is coming in and going out on average from these various routes, I find very intriguing and thought-provoking. So there's two distinct strategies, right? There's the carbon dioxide removal, and there's the solar radiation management, which can be on the ground, can be altering the atmosphere, can be launching mirrors, parking things at orbital points to try. I mean, there are many things that have been proposed. And people from 2009, have been just documenting some of the interesting ideas out there. And it's fascinating reading. One thing that got a lot of attention was Mount Pinatubo, was volcanoes. Because it turns out that if you have aerosols, if you have particulates, if you have what volcanoes emit, you actually have cooling for a couple years afterwards. And that's kind of interesting. And people have even observed that as we cleaned up the pollution that was much more in my childhood than it is now of the sulfates that were around, it looks like a little bit of our temperature spike came from making it cleaner, because sulfates are actually very good at keeping things a little bit cooler. Just like CO2 and methane keep it warmer, sulfates keep it cooler. So the thought is, well, let's do this. And so I've been in workshops where people are seriously discussing this as like the main option. And it's tempting because you can see that it's the sort of thing that could work. You just need some aircraft there, who are capable of putting it up there, or float a balloon. You can, for not so much money, have a very worldwide impact. People like me worry a lot about, you can have a worldwide impact. And the exit plan is not, you can't just round up all those molecules, right? You have to wait for them to precipitate out of the air. And people are studying it very, very carefully to try to make sure we don't do something really silly. So Ken Caldera has been looking at this for years, and I really appreciate how he's trying to study this thoroughly so that when and if our backs are to the wall, we'll know what the risks are before somebody goes off and does this. And what many people mean by geoengineering when they say geoengineering is this particular solution is, well, what about, stratospheric sulfates? And so for him, turning on geoengineering has big effects very soon. Well, that's a positive feature. That's a good thing. But turning it back off, I find this very frightening. You return very quickly. Your temperature comes very close to this is what it originally would have been. It pops up there very quickly, quicker than it's doing now, putting even more pressure on species. So this, to me, is a very undesirable feature of having something that once you're doing it, you've kind of got to keep on doing it, or even if you find there's some unintended consequence, or you find that you're kind of in more sudden transitions than you were. So thankfully, people are looking carefully at that. There's a host of other things we could say about this, but I just wanted to give an intro about this. Many, many studies have been done. One that I really like of geoengineering is by another fellow from this area, Dr. Armin Nuckermans. And he like I, has an HP background, but he is working on something that John Latham proposed originally, and that is to try to put clouds where you want them to reflect. So instead of reflecting way up in the atmosphere or reflecting at the surface or with the ice, he wants to have clouds at a kind of intermediate area and have these reflect sunlight a lot. And what I really love about this is when you stop, you stop. You know, there's no residual problem. And what you're doing is you're making clouds, which are pretty, you know, ubiquitous, and putting them where you want them to. So I find this a fascinating one. It's, in my mind, one of the good guys. But what I would say is, as you are looking at what you want to do in this world of helping the planet, I mean, this really is the image, right? I got this off a greeting card, which I've tried hard to give credit to, but it's a fragile thing, and really carefully, will you carefully try? So here we now get into what I've been working on. So I looked at the ice albedo feedback effect. I think I'll run that movie, our short video of doom again, and anybody who wasn't here at the beginning could get to have the joy of trying to guess what on earth they're looking at. I think we've given you enough hints, though. So what you're looking at up here, it'll hopefully keep looping through, is you've got month and year up here. We're counting through from late 1979 through 2012, and we're looking down at the North Pole, and we're seeing bright reflective ice, which is the white. Basically, what we're really looking at is the age of sea ice. This is what these researchers were doing, was looking at the age. It happens that the older ice is, the brighter it is. Don't worry, we will cycle through again if you don't catch it all. And what we're finding is that every winter, you know, ice does grow back, but young ice is almost as dark as open ocean. And therefore not very good at reflecting sunlight. And so you'll see that over time, you know, you get into the 90s, we're getting less and less of this bright reflective ice back. To orient yourself, here's Alaska, Siberia, Canada, Greenland. And we're losing an awful lot of ice out the Fram Strait. And more of these black and red dots are appearing. What on earth are they? They're all the buoys that scientists were putting out there to try to figure out what's happening to the ice. So you see more and more data gathering happening here over time. So here's the last time through, I promise. You can just see this phenomenal shrinkage. We're down to 25% of the volume and 50% of the area we used to have back just a few decades ago, I think is the right way. Maybe I have those flipped. But at any rate, it's a profound change in just 3 decades of how much ice we have lost. Yes? How does time change?
How reflective the ice is.
Oh, thank you. Yes, excellent question. When you have a first-year ice, you get that sort of glare ice. So I promised that I would stop, but if I'm answering this, we'll let it keep running. You have that glare ice that you found on a road, maybe, or ice like you have in a hockey rink. It's very perfect. And that's what happens initially. You get a very perfect layer. As it goes through freeze-thaw cycles over years, you build up imperfections. You build up air pockets, water pockets, you know, junk. And it turns out it gets brighter and brighter over time. And that's what we've lost. And so, you know, what on earth do we do about that? It's hard to see it rebooting itself unless we make the world substantially colder place somehow. So that's a very interesting. This was put together by researchers Ignatius Rigger and John Wallace up at University of Washington, and it's really pretty key info. Back to the slideshow, which has disappeared. Come here. From current slide. So what's happening now as we're melting ice is that more and more, as it melts, we have more open ocean area. We have increased open ocean temperature. We have an increased absorption of solar energy. So it's this positive feedback loop. And any engineer in the room, I'm sure, positive feedback loop makes you go, wow, is it in the right direction? Well, I know it's not. Oh. And so this was back when I made this slide many, many years ago. You know, this was estimated to be about 20% of global temperature rise. Now it's estimated to be more like a third. And this was the IPCC, that report that I showed you some information from early on. This was their prediction for ice melt. So all of their prediction is all this blue. Oh, what happened? Oh, I know what happened there. And this red was their prediction. The red was the average of their predictions from, oh, I guess around 1950 to a while from now. And the change from the 1979 to 1990, you know, that was their baseline. What's the change been? And so we're down to, this is down to area of ice, and we're down to about 50%. I'm sorry for the jog there. I had resized it to let my blue line show up, of all things. And that meant that this added thing that I put in for the 2007 to 2012 data just has gotten displaced because I didn't realize I had messed up that formatting. But way, way worse than the most pessimistic predictions that the IPCC was making back as they were getting that particular assessment put together. So it's bad news. This is part of what people say about some of the projections that we're trying to work from are actually not concerned enough. Well, they're concerned, but not pessimistic enough. People are really trying to be deliberately conservative as they state this so that they're not alarming people needlessly. Oh, that's interesting. I didn't change the title either. My apologies. I just added this one today. This is about my work. I got an article written last year in Fast Company about my attempts to slow down the melt of the Arctic ice. And so I'll post that in our readings too. So what on earth am I doing? Because this is something also I want to share with you so you can see where I'm coming from and see as you're thinking, wow, I've got a great idea for, you fill in the blank. This is one person's journey, not particularly sophisticated in climate or business or politics to start with, but it's been a very interesting education. Yes, very much an engineer. And so, you know, it's one person's journey, and hopefully it's illustrative and interesting. I've been lucky enough, I conferred with climate scientists from the beginning because I sure didn't want to go astray. I'm very keenly aware I'm an engineer, not a climate scientist. But get beautiful quotes like this, that this is, you know, perhaps one of the most important things, half dozen or so most important things that might have an effect. And that kind of thing keeps you working those unpaid volunteer hours for years because it matters. Here's a couple of things harvested out of that video that I was showing you. So June 1980 compared to June 2002 compared to June 2012. There isn't much multi-year ice left here. And so what are we doing? Quite simply put, we're trying to figure out the right materials to reflect sunlight. So take the place of the disappearing ice. Use the skill set I happen to have and say, oh, that's a materials problem. And try to figure out what material would not be harmful to put there. And it looks like it's applicable to, you know, all kinds of areas. And I've been cooking this up since, you know, as I said at the beginning of this talk, you know, since feeling like a Mack truck was about to flatten me and I was standing between the little kid with the teddy bear. So what do? Well, you choose something that's going to be quite harmless, and you choose something inexpensive enough, and you do it in a way that you could undo it if you had to, because there'll always be some unintended consequence. How bad will it be, and should you undo it? And so my ground rules for a solution are basically, first the doctor, right? First, do no harm. Now make sure it's fast enough to do some good. I am perfectly aware that this is not the long-term solution, for instance. The long-term solution is getting the right energy mix, the right conservation solutions. But what I was concerned by is the decades it's going to take us to get there. And so the thought is this is a Band-Aid. This is a Band-Aid that should be able to be used to get us there, to give us a little more breathing room to get there. That's its sole purpose. Because if we keep on heating up, anything we put out there is going to eventually, you know, not do enough to solve this particular problem. But let's make it fast enough to do some good now. Sustainable, ecologically respectful, reversible, right? The first, do no harm. And it seems to me if you can do something and undo it, you get to be in the delightful place that engineers like to be. So here we are with temperature or CO2 on this axis, you know, an uncontrolled situation. And here we are, maybe we overcorrect things and we are in the next ice age, you know, the deadly ice age that Humble Oil was so happy that they were averting. That's overcorrected, right? How do we get out of that? If we do things that we could keep tweaking so that the argument is about, oh, I wish we went back to the 1970s instead of the 1980s, man, I would be one happy woman. So, you know, you want to make it so you can tweak it where you want to be. And so we've had many adventures over the years. We've been doing testing from our deck here in sunny Bay Area to testing up on a lake up in the Sierra Nevada mountains for a few years, working on instrumentation. Satish Chetty has been with me from year 2, so just a year into it, joined in to do instrumentation for us. And we've just been blasting away. Minnesota has been one of our very best test sites. This is in the backyard of a retired PhD chemist who was really handy with his workshop and really generous with his time. And we've put all kinds of test areas there, and there's one of Satish's newer buoys. And we've gotten really good data sets there. So there's the pond owner and his buddy and Satish and me again. Of course, advertising Cal, forgive me. And at that point, when I put that together, you know, 6 years of lab and field testing. And we just keep looking at what's the performance of these high albedo materials. Last year, we got a really, really nice set. You know, we took what had been sorting out to be the best materials over the previous few years and put them over wide areas of this pond with good segmentation in it so that we could see that it was delaying. The best materials were delaying the melt by several days. That may not sound like much, but in a small pond, that's indicative of doing really well. And in large, you know, in the Arctic itself, ice experts that I've been conferring with for years assure me that just a delay of a few weeks or an earlier start of a few weeks to keep the ice around a little bit longer could do a lot to slow down this, you know, seemingly inevitable feedback loop. Maybe we can start rebooting it. We even tested up in Barrow, Alaska last year, which was a real adventure, and the logistics are so tough that we're not sure that we have a usable data set out of it yet. But we've been through the experience of being a place where the GPS coordinates are not actually accurate for where the lakes are, where the Wi-Fi is really difficult to get your data out. You know, just a lot of learning about when you were on the very frontier. Barrow, Alaska is way up there. When you're on the very frontier, things that you take for granted are a little more difficult. And here are the stars of where we tested. We did once in Canada. We did a couple spots here in California, Minnesota, Barrow. And my brother's trying to talk me into testing in Maine, which I think would be a really good idea. So that's kind of where we have done testing to date. It's been fueled by the fact that this is powered on donations. And so though we are longing to test in Greenland, for instance, that's just too expensive. And so at this point, not a feasible option. What we're doing, because we're fueled on donations, because it's kind of a nonprofit mission to try to save the world's polar ice, there doesn't seem to be a profitable company out of that yet, is to finally allow myself to become distracted by going the indirect route of trying to conserve water. We've got a drought. It's getting our attention. And our techniques are very good at cooling water and reducing evaporation. So why don't we try to do something about that? And so that's what we have just started to seriously back up and formalize that data and go after some funding to try to demonstrate that. I mean, you all know, well, unless you've just recently come to California, we've had a horrific drought for 4 years, and we really need to do something about it. And the same techniques we're using to try to slow down ice melt actually would be terrific for this. So we've been lucky enough, actually, to bring somebody new into the team who's pictured there and sitting in this class, to take a really good data set for some of our materials out in a sunny parking lot nearby, and to really formalize this enough to have gone to a good water meeting last week by Sustainable Silicon Valley and start connecting with the NASA and state officials and, you know, state water officials to start figuring out how we're going to get funded to get this out on a reservoir. And as I said at the beginning, you know, my little preview, oh, don't do that to me, of saying that these guys who are putting black plastic balls out on their reservoir are actually some of the best news I've seen in a long time for us. Somebody was paying them to do that, I'm sure, or at least gave them permission. And this costs a lot. And we cost our materials that we've been using that we find perform really well, about 1/70th of the cost of this, about 1.5%. And our methods keep water cooler, whereas black plastic balls, I don't have their temperature data, but I would be quite positive, I'd be willing to bet many beers that they're heating their water and therefore harder on wildlife. So we're finding that to be an exciting approach, and that may generate us enough income from that to start actually moving on in a more far-reaching way to try to save the polar ice, which is a very essential lever in climate change. The idea of doing this rather than building a reservoir or a reverse osmosis plant, it's just, you can do it quickly. You can undo it if you need to. You can move it to the next drought-stricken place if we're in an El Nino year. It's got some big advantages. So thanks, and who has quite great?
When you were testing on like the ponds and in Alaska, what kind of materials exactly were you using?
Yes.
And do they decompose, or
Right.
do you have to go there and pick them back up?
So I like to think about this being, and I didn't get just a regular cup or anything. I like to think of the backpacker's ethos, right? Of you don't want to leave food around, you don't want to. One of my favorite types of materials, and the one that we've been working on for a long time, are variants of floating sand, hollow glass spheres. Because you don't really want, I think, to put a lot of organic there. You might need to put a little bit there as a binder. But sand, you can hardly get more harmless than that. SiO2, I mean, it's everywhere. And you can get various forms of hollow, yeah, you can pass this around, of hollow glass spheres, or these aren't particularly spheres, these are a larger version, that are reflective. So they're relatively high albedo. They're certainly higher albedo than open ocean, that float. And what we find in that Minnesota pond is that as it has a really attractive feature. As we go through freeze-thaw cycles, which you do in the spring, so you can see the various materials that were there, and this was the best one. As you go through those various freeze-thaw cycles, the hollow glass spheres tend to come to the top, which is exactly where they're needed. We've tried a number of other types of materials. The most miserable winter of my life was putting sheets around. I can really understand one of the reasons why, if Jason Box thought that that was the best thing that you could possibly do for saving ice, and there he was on the Discovery Channel nailing these sheets into Greenland. Well, with my smaller experiences on the lake up in the California Sierra Nevada mountains, and then over there in Minnesota, I mean, it's horrific when you're putting these big masses of sheets surrounding your instrumentation buoy, going back up there, in your spare time to see how it's doing and find it's always shifted. There is no way to effectively anchor it, which tells you that, surely eventually you could solve that problem too, but it's going to cost a lot. And so I'm very, very fond of these particular types of materials, these hollow glass spheres. They behave pretty darn well. So that's the play. And they're used in everything. They're used in building materials to make things, and they're used in lots of materials to make them lighter and to make them less thermally conductive for good heat insulation. So you can buy them, all kinds of them.
Do they decompose?
Well, they can fall apart. The ones I'm passing around is actually a variant on that. It's not strictly spheres. It's a post-consumer recycled glass, where it's been composited by this one company. And so it floats not from a hollow gas core, which is what hollow glass spheres will do, the formal hollow glass spheres, which can be pretty indestructible. I mean, you could drive a truck over those. But these will keep abrading against each other, and eventually you open up those pores, and then they will sink. And you can choose ones intentionally that will sink over time if you're concerned about having it float forever. I mean, there's all kinds of things that you can do to help minimize your environmental impact on it. The first thing that we really wanted to know is, do we have something that slows down and that looks economical? And yeah, we think we do. So there's a lot of testing left to be done. Any other questions? Yes?
So if you, let's say, can apply those to the glacier itself or the ocean, will it have any impact underneath the sort of like layer of silicons?
You know, I used to show a slide that I've realized as I try to pack more and more intro stuff into this, I get this shorter and shorter. But one slide that I put in that I really take very seriously is this beautiful graphic somebody put out years ago of the undersea life, even in the Arctic. I mean, it is a rich ecosystem under there. And so one of the things that I think is very important is to not, I mean, this is not how I would actually want to do it. I do not want to carpet the whole thing. This looks so regular because Tony, as he put this stuff out, you know, had these 5 foot on a side, well, we were reusing the frames, and spread them in there so it looks like a carpet, but it's actually all these individual balls. But what I would like to see are areas that are covered and areas that are not, because I think that's important. And I think it's important that if you have things as close as you can get to a monolayer, you're also going to have, even in the middle of your densely covered area, you're going to have areas where sunlight can get through too. Because it would, yeah, it would not be doing you a favor to just suffocate it all. It would be almost as bad as the orbiting solar mirrors, right? But you'd be doing it more locally on your ocean surface. No, I saw somebody holding it up to light. Any other questions? These are good questions. Yes?
Can you talk more about the policy and challenges related to actually implementing the solution if you find out that it really is very effective?
Well, if I knew the answer to that, boy. So what we've, right, and that's part of, you know, part of what you get here is somebody who honestly is trying to figure her way through this and who is an engineer, not a politician. I think our first step, and I really think it's a good one, is to prove this out on water and to try to help this. I think is going to be a very good step towards gaining acceptance for these materials. There's a great deal of water quality testing we should do. Those of you who are materials gurus or materials literate know an MSDS, right? Material Safety Data Sheet goes with every chemical, every compound. And the MSDS for what we're using comes up very, very clean. And we had no trouble getting permission to use our types of materials on that lake up in the Sierra Nevada mountains that was actually people's drinking water. And they never had an issue. I mean, it was from their water district that gave us their permission. So the materials are good, but from that standpoint, as far as we know so far, but to be able to prove those out on a fair-sized region and have people see that and see it cooling things and saving water, I think would be a big step up for us. That's one of the really important steps. We have had, so part of what I didn't tell the story here that I guess I could have talked slower or included more, was that we've been through a couple of business accelerators, the Clean Tech Open, Sustainable Silicon Valley, and made a lot of connections there. And we've had a number of really nice conversations with people at NASA who have had a sustainability effort which really seems aimed at helping to leverage people like us with all that amazing infrastructure that they have, right? And so the hope is that at some point we will be able to collaborate with somebody like that who could perhaps monitor our tests as sort of a fair broker, you know, as an impartial judge. I've been very excited. Our water speaker who's coming in a couple of weeks was a second-level referral for us from Felicia Marcus. I mean, it's time now for me to reach out to people like Felicia Marcus, and I've done so. Who is she? She's the head of the California Water Resources Board, and she's been giving talks to the MIT Club and Actera and the Dartmouth Alumni Group, and just, she is really great. She's a policymaker. She is the head of the Water Resources Board, but she's very technically comfortable and very brilliant woman. And so people like that, you know, trying to make connections like that. But I don't know a magic bullet. The puzzle that you'll see as you go through, yeah, I started to read. I have a bunch of books you guys are welcome to borrow one at a time if you're sure you're taking the class and you're sure you'll bring it back. So Elizabeth Colbert is very, very vocal about the politics and the horrors of, the sixth extinction that we're in the middle of. The second third of this book, The Global Warming Reader, is all about the politics. So I'll probably be learning along with you about that, because so far what I know about the politics is it's hard. And it's hard for a number of reasons, but it's hard. But I do see hope, those news snippets that I was showing you, more people are paying attention to it. Is anybody in here actually a political expert or a policy person?
I'm an advisor to an ambassador.
Whoa! Where? Could it be Denmark or
Palau.
Greenland? Palau.
Palau, small island state in the Western Pacific.
Small island state. We should talk.
Not sea ice, but.
Oh, but that's interesting. But rising sea levels is a horror for them, right? Wow. And so what advice do you have to offer us?
Well,
Your expertise is greater than mine.
well,
I'll take a seat.
I can tell you from Palau and other small island states I worked with the UN this summer.
Whoa, okay.
Those are the locations where I guess the most outrageous or the most extreme examples of ingenuity, including engineering ingenuity and other political types of strategies to combat like climate change and adaptation strategies. That's the location where those strategies are taking place, because it's life. It's I hate to paint in these terms, but it's life or death.
Well, it
this
is.
is like Palau. So they're taking more extreme measures. With this type of technology, I know it's not applicable to small island states. We're talking tropical locations here, but those are the politicians that are more amenable to employing strategies like this. There's different challenges there as well, but when you're trying to find the places where these things or steps are being made, progress is being made in the positive direction, you look to the places that are going to be most directly and adversely affected by climate change. So Palau is one of that's part of the reason why I'm working for this ambassador now.
I hope you signed our list and are really taking the course, are you?
I am.
Yeah, oh, great. Wow. That's a nice perspective. Anybody else have a policy insight or connection? That we should be sure you participate every single class. Give some advice here. This is good.
Well, leading up to the COP, a lot of the stuff is really important. We're talking. I've been working for her for almost a year now, and it's ramping up to the COP. There's some people are optimistic about it. She is my ambassador is less so for different reasons. So I can give you a certain perspective.
Got at least 2 minutes here if you want. Or you can be more prepared for next time. Oh, that's great. Thank you. Wow, that is one thing I love about this class. Yes?
So I was wondering if you've encountered any unexpected environmental consequences of the technology you're developing, or if you haven't gotten there yet.
So if we did, we'd pay attention, right? We have found that one kind of material that we've been using, we found this again in our little pools test recently, has this tendency to just migrate to the side, no matter what you do. And it's one of the things that we deployed in Minnesota, but we didn't notice it during the season in Minnesota because we deployed while things were frozen. And when so at the end of the season, this mysterious thing, we couldn't find where it had gone anymore. I mean, we could find this, but a different material that wasn't quite as bright. We just couldn't find it afterwards. Well, that's intriguing. But it's fundamentally sand, so okay, it's not going to do anything. In a pool, little waiting pool in a parking lot, a bunch of them with identical conditions, just testing cooling. What we were finding was that they would, within rather short order, find themselves clinging to the side. And it's like you've got this vast open space in the middle, and it's all clustered to the side. And it was the same stuff that had disappeared in Minnesota after the melt. And it's like, oh. But, is that an environmental consequence? No, but it says that's not one of our first choice materials because it's not going to do much good for at least after the melt. I mean, that's the point of having chosen this family, is it's hard to see what it's going to do unless, and here's the thing we need much more info on, is there a size range, and you can get a variety of size ranges of these, is there a size range where it's going to get ingested by somebody? And is that harmful? It may not be. Some creatures intentionally eat sand or small rocks, you know. And so if it passes right on through, you might be okay. Or it might be that in your particular ecosystem, you might want to, you know, compound things to have them bigger, or you might want to intentionally use teeny. So that's the kind of things I think are going to get the complex on-the-spot considerations we're going to need. Yes?
So when you're going to like the North Pole, per se, and you get on top of a glacier, would you see this on a large scale, like taking a bag of those things that with a water bottle and like pouring it out on top of the glacier?
Oh, there were years past when I was early in this project when I could picture myself just taking a suitcase full and then spending undoubtedly the rest of my life in jail. But it's like, but I was trying to do a good thing. So I haven't done that. I did not fall prey to that temptation. But that is, you're bringing a very important point. You would probably think, given the way that I'm thinking, that I would want to spread this all over the Arctic. And that's not the right thing. The thing is to find the essential spots. And so some of the spots that I think might really benefit, polar bear breeding ground. Hudson Bay is the main polar bear breeding ground in the world. That Fram Strait, where we saw all that ice disappearing in the 30-something second video of doom, might be a really tempting place to put some of this to try to be a fluidic constrictor, basically. But to put it everywhere would be insane. And remember, you're going to have to allow for shipping lanes, because people have gotten very excited that there could be shipping lanes, and I'm not going to fight that. You know, it's like, okay, but let us save enough to slow down the, you know, the planetary warming problem. I saw another hand.
How can you make sure that it stays in the right spot? And if it's flowing away, how can you like calculate, like influence that kind of stuff?
Yeah. So when you're
like after the melting.
Yes, when you're testing in a small contained body of water, no issue. But if you were out on the open ocean, oh heavens, how are you going to figure it out, right? I mean, here when it's frozen, you can easily fence it. But after the melt, where does it go? And so if you're concerned about that, and if you're thinking that it's going to melt every season, if you're in a place where it's going to do that, then you do have a couple choices. You can say, well, it's going to roam free and it's going to do good somewhere else. Or you can, right, I mean, well, it's almost like raising children. Go forth, do good things. Or you can engineer it to sink after a season. Right? And so you choose the fragile one, not the one that you can run a truck over. Those are really important questions. They are really important questions.
Because otherwise you have like all the stuff on the ground of the ocean, so maybe it will influence them. They're coming.
But if it's sand, right? And if you're fundamentally trying to work in, I mean, that's an important point, is we're trying to put as small a material load as possible to do the most good. So we're talking about a monolayer. And so that's, you know, tens of microns, hundreds of microns thick. It's not much material. And so that's the other thing that keeps, that's why our economics are better than big 4-inch black plastic balls, for instance, right? We're trying to do more with less. And so it seems like a minimal impact, certainly compared to the loss of the ice, which has been a major impact. So, but these are great questions. These are the kinds of things that, yeah, we have to worry about and have been worrying about for a long time.